So in this section, we're going to be graphing some rational functions, and then we're going to graph some stranger looking functions. We're going to start with this one, graph f of x equals x squared plus 3 over x by finding the asymptotes, the intercepts, the intervals of increase and decrease, any extrema, the intervals of concavity, and any inflection points. So you should recognize that the intervals of increase and decrease and the extrema are going to come from the first derivative. The intervals of concavity and inflection points are going to come from the second derivative. Some of finding the asymptotes, though, we're going to get from something we've done earlier this semester. The second part, though, we need to be reminded of some algebra skills. And then our intercepts, we need to go back to algebra skills. So let's start with asymptotes. Recall in college algebra that to find vertical asymptotes, you set the denominator to 0. So our denominator is an x, so we're going to set x to 0. Now, recall that we always have to check this in the numerator. If this value makes the numerator 0, then it's not a vertical asymptote, it's a hole in the graph. So if I look up here, 0 squared plus 3 is not 0, it's 3. So this is a vertical asymptote, and I'm just going to abbreviate it VA for vertical asymptote. And that's the actual equation to that vertical asymptote, x equals 0. All right, now, to get horizontal asymptotes, we're going to use calculus. And we're going to use limits that we did earlier in the semester. We are going to take the limit as x goes to infinity of our function. We also have to do the limit as x goes to negative infinity. And this will yield any vertical or any horizontal asymptotes we might have. Now, sometimes these two limits will be the same when we do the limit from as x approaches negative infinity. Sometimes it'll be different. In this case, I think we'll see that the limit is different. Let's recall how to find the limit as x approaches infinity, though, for a fraction. Recall what we do is we look at the denominator, and whatever the highest power is on x, we're going to divide by the x to that power. And we're going to divide every single term. So we're going to take our x squared and divide it by x. We're going to take our 3 and divide it by x. And on the bottom, we're going to take our x and divide it by x. Now let's go through and let's reduce everything that we can reduce in this. Alright, so x squared divided by x is just x. 3 over x will not reduce. But on the bottom, x over x will reduce to 1. Alright, now, recall, as x goes to infinity, any fraction that has x in the denominator will go to 0. So 3 over x is going to go to 0. 1 on the bottom is going to go to 1. And then x, as we put really large values in, is going to go to really large values. So this is going to infinity. Okay, so that's not yielding us a horizontal asymptote. Now let's do the other limit that we have to do, and that's the limit as x approaches negative infinity. Now we can skip our first steps. We're still going to do exactly the same thing. So really, we just need to put this right here, the already reduced form right here, and think about what happens as we put negative infinity in. This is still going to go to 0. This is still going to go to 1. But as we put large negatives into x, it's going to go to negative infinity. Let's notice that this did not yield us numerical answers. So we don't have a horizontal asymptote. As we go out the x-axis on the right side, our y values are going upward. And as we go out the x-axis on the left side, our y values are going downward. They're not going toward a specific value. Now, if this had been a 2, for example, then y equals 2 would have been a horizontal asymptote. And similarly here. Okay, so no horizontal asymptotes. Let's go to the intercepts. And here's where we go back to college algebra again. To find a y-intercept, we put 0 in for x. But let's notice here that the 0 for x in the denominator was actually an undefined value. That's where our vertical asymptote is. So there is no y-intercept. To find x-intercepts, we set the whole thing to 0, or we set f of x to 0. So if I set f of x to 0, I put a 0 where f of x is, what I'm wanting to know is how to solve that. Alright, now, recall though, the denominator is not allowed to be 0. That is our vertical asymptote. So a fraction is equal to 0 only when the numerator is equal to 0. So let's set our numerator to 0, and that's our shortcut for finding an x-intercept when dealing with rational functions. All we have to do is set our numerator to 0. So if we attempt to solve this, move our 3, and take the square root. Don't forget there's both a positive and a negative square root. We know in the real number system, we're not allowed to take the square root of a negative number. And since we're graphing, we're definitely in the real number system. So this really has no solution in the real number system. There are no x-intercepts. This graph, will not cross the x-axis. It will not cross the y-axis. Okay, now, we've got our asymptotes, we've got our intercepts. Let's go to our first derivative and intervals of increase and decrease in any extrema. All right, so this is a rational function. We have to use our difference quotient. I'm sorry, not our difference quotient. Our quotient rule. Okay, so let's take the derivative of the top. So the derivative of x squared plus 3 is 2x. So we will have first derivative. We get 2x. And then we want the bottom to tag along. And the bottom is just x. Now we want the derivative of the bottom. Well, the derivative of x is just 1. And then the top will tag along. And then all of this goes over the bottom squared. And since our denominator is x, that will be x squared. All right, now, it's very important to clean up these rational functions derivatives. So, let's see, we'll have 2x squared minus x squared, and take that minus sign through, minus 3 over x squared. That gives me an x squared minus 3 on top over x squared. Okay, so we need to determine when this function is equal to 0. We also need to determine when this function is undefined in order to find the critical values where it's undefined. All right, so we need to set both the top and the bottom to 0. Now let's notice that this one is going to lead me to 2 critical values, the positive and negative square root of 3. Now, for the sake of graphing this in a few minutes, I am going to go ahead and get the decimal version of the square root of 3. And we're just going to round this to positive and negative 1.7. All right, now, if we set the bottom to 0, we're going to get 0. And you may remember that 0 is a vertical asymptote. So it's important to keep that in mind. But we do have to put it on our sign chart. So let's make our sign chart. And I'll put these in order. I'll have negative 1.7. I'll have 0. and I'll have positive 1.7. Okay, so if I choose something to the left of negative 1.7, let's say negative 3, and I plug that here, and be sure to plug it here, all right, into our reduced version of the fraction. So let's say I put negative 3 in here. I'll have 9 minus 3, that's positive on top. And if I put it in the bottom, negative 3 squared is positive also. Positive over positive, this will be positive. All right, now let's choose something in between negative 1.7 and 0. Let's say negative 1. If I put that in here, I'll have 1 minus 3, that's negative on top. And negative 1 squared will be positive. So negative over positive, this is negative. If I choose something between 0 and 1.7, let's say a 1, I'll have 1 minus 3, again negative, over 1 squared, which is positive. Negative over positive will be negative. And finally, if I choose something over here, let's say a 3, I'll have 9 minus 3, positive again, over 9, positive over positive is positive. Now be careful, that 0 has to go on this chart, and it's very important that we remember that it's a vertical asymptote. Things can be different signs on either side of an asymptote as we decide increasing and decreasing. All right, so let's notice this graph is increasing from negative infinity to negative 1.7. And it's also increasing from 1.7 to infinity. And then let's notice, and unfortunately Word is messing up on me, so I'm going to have to kind of flip back and forth. From negative 1.7 to 0, and then from 0 to 1.7, the graph is decreasing. So let me write that down. So negative 1.7 to 0. And from 0 to 1.7, the graph is decreasing. Now let's look at our extrema here. All right, so going back. All right, so let's remember this is a vertical asymptote. So no point will occur at this 0. We don't need to consider it for whether or not it's extrema. Here, though, we have that the graph is, and I don't know why this is acting up on me, increasing and then decreasing. So we have a max at negative 1.7. And then over here at positive 1.7, it's decreasing beforehand and increasing after. So we see that that's in a valley, so that's a min. Let's find the corresponding y values that go with this max and this min. Plug back into the original function. So this first one, if we plug into the original function, is going to give us, if I round to 1 decimal place, negative 3.5. And then this one will be positive 3.5. And let's see, if we go back, the negative 1.7, looking at the sign chart, was a max, and this was a min. And you might think, well, that's strange, but we'll see when we graph this how that works out. So this one is actually the max, and this one is the min. Now I'll have to go to another video because YouTube will only allow me a 15-minute video, so we'll do the second derivative on the next video.